Our whole world is running on a set of rules we can't even see. I mean, think about it. From the phone in your pocket to a bolt of lightning, it's all governed by these invisible forces. So, today, let's pull back the curtain and take a look at the secret rule book for electricity.
And that's really the big question, isn't it? What are these rules? How did tiny particles manage to talk to each other across totally empty space and create all the amazing stuff we see? Well, that's the mystery we're going to unravel in this explainer.
All right, to get a handle on the language of electricity, we have to start with its most basic building block. Its fundamental atom, you could say. And that's a property we call electric charge. Seriously, everything else is built right on top of this one idea. Now, here's the first weird thing about charge. It's not like pouring water, where you can have any random amount. Nope, it's more like money. You can have $1 or $2 or $1,000,000, but you can't have half a dollar. It comes in chunks. This is called quantization. It means the total charge, Q, is always a whole number, N, times the charge of one single electron, E. It always comes in these neat, countable packets. Okay, so we've got these little packets of charge. Now what? The next huge question is, how do they talk to each other? How does one charge over here even know another one is way over there? Turns out, they have a very, very specific way of interacting. And the rulebook for that conversation? It's right here. It's called Coulomb's law. Now, don't let all the math on the page freak you out. The core idea is actually pretty simple. It's just a super precise rule that tells us exactly how strong the push or pull, the force, is between any two charges. It's not random at all. It's totally predictable. Let's just break that down real quick. The force, that's F, really depends on two big things. First, how much charge you have on each object. That's Q1 and Q2. The more charge, the more force. Makes sense. Second, the distance between them, which we call R. And just like gravity, the farther apart they get, the weaker the force gets. It drops off really fast, actually. Okay, so charges push and pull on each other. Got it. But what if a charge is just sitting there, all by itself? Is it doing anything? This is where a really beautiful idea comes into play. Physicists started to think, what if a charge changes the very space around it? And that change, that influence, is called the electric field. Think of it like a charge's aura. It's this invisible map of influence that surrounds it, filling all of space. It shows the force that a tiny little positive test charge would feel if you dropped it in at any point. So get this, the field is there, even if nothing's there to feel it. And to help us see this invisible field, we draw lines. A single positive charge has field lines that just shoot straight out, kind of like rays from the sun. But then you bring a negative charge nearby, and their fields mix and merge, creating these incredible, complex patterns. This is how the simple chat between two charges can grow into a whole symphony. This is all really cool, but you're probably thinking, okay, but how do you actually measure this invisible field? How do you put a number on it? We need a way to count it somehow. And the way we do it is, well, it's pretty clever. Imagine you're holding up a window frame in a storm. The more wind that blows through the frame, the stronger the wind, right? We do the exact same thing here. We imagine a surface, and we just count how many of those electric field lines poke through it. And that's the key. That count of field lines passing through a surface has a special name. It's called electric flux. Just think of it as a measure of flow. The more lines passing through, the higher the flux, and that tells you the electric field is stronger right there. It's our tool for measuring the invisible. Now, you can imagine that for some really complicated situations, trying to count all those lines would be a total nightmare. But luckily for us, there's a shortcut, a kind of master key that makes really hard problems suddenly easy. It's called Gauss's law. Gauss's law gives us this just mind-blowing insight. It says if you imagine a completely closed net, like a bag you could zip up, the total number of field lines poking out of that net tells you exactly how much charge you've caught inside it. And that's it. What's happening outside the net doesn't matter at all, only what you've enclosed. So how do we actually use this? Well, it's a brilliant little recipe. First, you pick an imaginary shape that's nice and symmetrical, something that makes the math easy. Then you figure out the flux, the lines poking through your shape. You use Gauss's law to connect that flux to the charge inside, and bam, you can solve for the electric field, E, in a way that would have been impossible before. I know this might still sound a little abstract, but trust me, when you start using this master key, it unlocks some truly amazing and sometimes totally weird things about how our universe works. Let's look at one of the most famous results.
So let's use the key. Imagine you've got a hollow metal ball, and you cover its surface evenly with electric charge. Now, what's the electric field like inside that hollow ball? You'd think it would be crazy in there, but Gauss's law gives us a stunningly simple answer. It's zero. Absolutely nothing. Nada.
So, how is that possible? Why is it zero? Well, imagine you're standing anywhere inside that sphere. The strong pull from the few charges that are really close to you is perfectly, and I mean perfectly, canceled out by the weaker pull from all the other charges that are farther away on the other side. Everything just balances out. It's like being in the calm, quiet eye of a hurricane.
So there you have it. We've gone all the way from a single little packet of charge to understanding why you're actually perfectly safe from lightning if you're inside a car. It's basically a metal sphere. These are the invisible rules. And it just leaves you wondering, doesn't it? If we can find this much elegance and beauty in just this one area, what other incredible, invisible laws are still out there, just waiting for us to find the right key?